Hello again. I'm going to go over chapter 2 now, which is all about chemistry. So don't get scared because the chemistry here isn't really that bad. And there's a lot of memes here that hopefully will make you laugh. But this chemistry isn't that bad. It's just the kind of basic chemistry you've been through before. What is chemistry? This is just the study of interactions between matter and energy. We typically know what energy is in my classes, so we go over more in depth what matter is. But energy is just the ability to do work, or just how things are powered in life. Matter is here we go, anything that occupies space and has mass. So if it has those two qualities, it is matter. In class, we do the is it matter activity where the students have to sort a list whether it's matter or not matter. Things that are not matter would be like light, sound, wind. Those are the movement of things. What would be matter? I use like a desk, a dog, just anything that has mass and takes up space. Next, we move on to elements. Elements are substances that cannot be broken down into simpler substances. They can be broken down, however, like into protons, neutrons, and electrons, which we will get to next. However, those substances won't have the same properties as the elements. So you can break down carbon, but once you break down carbon into protons, neutrons, and electrons, it's not going to have the same kind of properties as it did before. Element symbol, this is just the abbreviation for that element. For example, hydrogen has the one letter H and helium has the two letters HE, and that second letter is always lowercase, while the first letter is always capitalized. You should know this stuff from your 9th and 10th grade or your middle school science classes. Atoms, these are the smallest part of an element. You can't get smaller than an atom without breaking it up and then kind of losing some of the properties of that atom. It's the basic unit of matter, but one thing I want you to make sure you understand, it is not living. Not living. A lot of people think that these are living, way too small. Uh, Atoms are made of three parts. These are called subatomic, so think sub, below, atomic, that's the atom. Particles. Protons are positively charged. They're going to be found in the nucleus. Electrons are negatively charged. They're going to be found around the nucleus. They are in these things called orbitals, which we'll get to next. And neutrons don't have a charge, and they're also found in the nucleus. You can see here, I'm going to bring up more notes. There we go. The nucleus, again, has the protons and neutrons. They're tightly packed together and they're very dense. And the electron orbitals, this is where the electrons are. This image isn't the best image to use for an atom. I still use it just to talk about it because a lot of people think then the atom is very large and like the nucleus is very large. To give you an example, if the atom was as large as like a baseball stadium, the nucleus would be as big as a marble. That's how small the nucleus is. And the electrons would be like pieces of dirt flying in the outfield. So like these things are very small. And that's because an atom is mostly made up of empty space. This is kind of what an atom looks like, more realistic, but again, still it'd be even smaller than what you have here. The atomic number, this represents the number of protons in the nucleus. We can see here this is helium. So that means helium has 2 protons in its nucleus, which means the atomic number will be 2. We find the atomic number above the element symbol on a periodic table. The atomic mass, this is the weight of a single atom. In the atomic mass, we usually only weigh the protons and neutrons. That's because the electrons weigh so insignificant compared to these two. We just don't include them. So we're just really weighing the nucleus of an atom. Let me go back here. There we go. So again, you might see these cards or these kind of squares on the periodic table. The atomic number is above. The element symbol here you can see is below the atomic number. The element name is usually below that. And the atomic mass or weight is usually at the bottom here. So again, in this instance, the atomic number for oxygen is 8, while the atomic weight or the mass is 16. And in this case, that means there are 8 protons in the nucleus of oxygen. Now, talking about the atomic mass weight of these different subatomic particles, we give the atomic mass of a proton 1, same as a neutron 1. The electrons don't have an atomic mass unit. That's because they're just so insignificant. They do weigh something, but they're just so small, it really doesn't matter for us. So again, 1 for both protons and neutrons, 0 for electrons. All right. So the periodic table has 118 elements, and this is organized by the atomic number. You've probably seen the periodic table before, but here it is. You can see the atomic number starts up here with 1, then goes to 2, 3, 4, and it goes all the way down to 118. This one actually might not. Yeah, I think this. Oh no, this one does. This one goes 118. The one in my classroom, the big one, is a little bit old, and it only goes to about 112. That's because these last couple elements have been kind of created by man, and they're still in the process of verifying them, but they're not naturally occurring. I think it's only like 92 or 94 are naturally occurring on Earth. Valence electrons, these are the electrons on the outermost orbital of the atom, and these electrons help the atom bond with other atoms. There can be a range of 1 to 8. I don't typically go over valence electrons a lot in my class. All I want you to know is the electrons are what's going to be the subatomic particle that actually deals with the bonding of atoms. You can find the valence electrons by looking at these groups here. You can find this row is 1, this row is 2, 3, 4, 5, 6, 7, and 8. But remember, the helium only has 2 because it kind of should be over on this side, but they group it usually over here with the noble gases. Now, chemical bonds, these are bonds that are, let me go back. These are going to be bonds that hold, or forces that hold compounds together. They typically are again, because of the electrons interacting with each other. This oxygen right here is bonded to 2 hydrogens. This is water. You can see this is carbon dioxide, and here's another. I think this is propane, C8 or C3H8. Now, compounds are, I'm going to skip over here actually before we get to compounds. I'm going to go over what a molecule is. Molecules are going to be held together by a covalent bond, and they're usually at least 2 atoms held together. The difference is a molecule can be just the same element. So you can have like oxygen, O2, and it be a molecule. So all compounds are molecules, but not all molecules are compounds. Let me go back here, and I'm going to show you what compounds are. Compounds are substances that contain at least 2 different elements. So like water is a compound and a molecule because it has at least 2 atoms and at least has 2 elements. You can see this oxygen, these 2 hydrogens here. This is glucose. This is also a compound. We're going to be looking at more at glucose later on this year. Now, a compound will differ from the individual elements. So like sodium here, this is a element that when you put it in water, it explodes, and chlorine is a deadly gas. But when we put them together, we get salt. That's what happens. When we add elements together, their properties start to change. So don't think that just because an element does one thing, when you put it in something else, it will do that same thing. Those properties are going to change. We know what a molecule is. Now, the difference between a molecular formula and a molecular structure is the molecular formula shows you what elements and how many of each elements are in those compounds. The molecular structure is the arrangement of these atoms. So we can see here C4H10, this is butane, this is the molecular structure, this is the molecular formula. So this just tells us what's in it. This tells us how many or how the atoms are arranged. Now, the 2 different types of bonds we're going to quickly talk about are ionic and covalent bonds. These are, again, bonds that are going to work with how the electrons are interacting with each other through the different atoms. Let's go on to the first one. Here we go. Ionic bonds. These are when atoms tend to give up or accept electrons. And this is what sodium chloride is. This is what salt is. Sodium is going to give that 1 electron to chlorine because that chlorine wants the 1 electron to fill its outer shell. What happens here is these create ions, and the ions then are the attraction forces that are going to hold these bonds together. So then what happens is you get a positive ion and a negative ion, and these are weaker bonds because they're just like a little bit of an attraction force. I talk about how this is like when 2 magnets are kind of pulled towards each other. Covalent bonds are when you have the electrons being shared. So like water is an example of this. The water molecule here is held together by these 2 electrons being shared between the hydrogens and the oxygen. These are usually stronger bonds. Oxygen is another example of a covalent bond where you have these 4 electrons being shared between these 2 oxygens. Remember, ionic, give, covalent, share. That's my I always say ionic, give, covalent, share. Now, water. Water is a really cool molecule. This is again, molecule that you're going to have all throughout your body, and a cell is mostly made up of water. Water is polar, which means there's an unequal sharing of electrons. We don't usually get into that kind of deep concept with water, but understand water is polar, and it will break down a lot of other polar molecules. It's known as the universal solvent just because a lot of molecules are polar. And what happens is the nonpolar ones don't dissolve in water. So like lipids, fats, waxes, things like that don't dissolve in water and don't mix, those are nonpolar. Water creates hydrogen bonds, and these are like little dots, or these are represented by little dots between the water molecules. This is a very weak bond. Um, but yeah, these form between the water molecules, and this creates some of that surface tension that we are going to talk about in class and go over. But they're just a attraction force between the water molecules. I typically tell the students that the hydrogen bonds are the weakest, ionic bonds are a little bit stronger, and covalent bonds are the strongest. There is some variation here. There are some ionic bonds that are stronger than covalent bonds, but mostly the hydrogen bonds are the weakest. Ionic are a little bit stronger, and covalent are the strongest. All right, cohesion versus adhesion. Water molecules that stick together, that's cohesion. That's that traction force between the water molecules because of those hydrogen bonding. Adhesion is when water molecules stick to other molecules that are not water. So if you look up here, this is cohesion, water molecules attracting to each other, and then adhesion, water molecules attracting to the non-water molecules. Surface tension, there's a high surface tension that is created by water. It's because of all of the water molecules just being so small and attracted to each other that it creates this high surface tension. And what we see is like insects and different things using this high surface tension to kind of skim across the water. And there's a lot else that goes on with this high surface tension, but this surface tension is just due to that cohesive properties of water. Water density, and I realize I am going through this kind of quickly, but you should have seen this stuff back in like middle school science. So this is kind of a review. Water is less dense as a solid. So again, the ice that floats, it's less dense because the water molecules, when frozen, they're actually pushed away from each other, and they create this kind of like lattice or this crystalline structure, and that makes it less dense. So that means that the ice then floats. And I know it's like, oh wow, this is ice that floats. Like no, I know this. But this is kind of rare in science, where we have the solid actually being less dense. It's usually more dense, which makes it sink. In this case, it doesn't. It does the reverse. Acids and bases. So the pH scale measured acids and bases, and it goes from 0 to 14. 0 to 7 is acidic, 7 is neutral, and 7 to 14 is basic. So if you fall within this range, you're acidic. If you fall within this range, you're basic. And 7 here is neutral, which is water. The pH scale, the pH inside most cells is 7 because water is 7, and most cells are mostly made up of water. What we mean by acids and bases is the hydrogen versus the hydroxyl ion concentration. So what this means is acids have more hydrogen ions, bases have more hydroxyl ions, and the neutral solutions have even amounts. You can see here there's more H's here, there's more OH's here in the basic solution, and in this neutral solution there are even amounts. So again, just like I said, acids have more hydrogen ions, bases have more hydroxyl, and those neutral pHs have that even amount of hydrogen and hydroxyl. Heat capacity of water. Water holds on to a ton of heat very well. A majority of the heat from global warming is captured by the oceans. Oceans are a big heat sink in the world. They just capture a lot of heat. And you can see here water's heat capacity is more than 4 times than most metals. That makes water very unique. Lastly, a couple more terms here that you should know. Solute, solvent, and solution. Solute is the material that's dissolved in solution. Solvent is the substance that's being dissolved. And the solution is just that combination. So I always talk about this as like Kool-Aid powder. This is your water, and this is your actual Kool-Aid that you can drink. So the Kool-Aid is the actual powder is your solute. The solvent is the water, and then the solution is what you can drink. Lastly, an aqueous solution just means any solution that has water in it. Whenever it's an aqueous solution like Kool-Aid, that's just the water is the solvent. Water is a universal solvent, which means it can dissolve most polar things, and it can dissolve a lot of things in life.